Thanks for organizing all this wonderful workshop. I've been having a lot of fun listening to everybody, and uh, I should mention, just like what Srijit was saying, I've had a lot of fun visiting IIT Hyderabad every time I go to India, and we've also had many student exchanges, and I've been also talking to some people regularly. So it's been quite a lot of good stuff coming out of this collaboration, and I hope that this will continue in the coming years. So I wanted to talk about some recent things that we've been doing on this theme of adaptive Bayesian intelligence and thinking about how it can help us to get to sustainable AI systems. And I'll basically give you a summary of that work. Um, so I think most of us can agree that the way we are training AI models right now is unsustainable because we really require a huge amount of, sorry, is there a, okay, so this is not a question for me. So what I was saying is that right now to train AI systems, we require a huge amount of data, compute, and infrastructure, which is extremely costly and unaffordable. And it will be great if we can somehow reduce the dependence on this large infrastructure that only some of the big players in the game can afford. And it's creating a big monopoly and also probably not very good for the environment. So we've been thinking about the reasons why training AI systems right now is so computationally heavy, is unsustainable. This is really unlike how humans learn. And this video, if you've seen my talks before, this is my daughter learning, and I'm sorry if I'm showing this for the 100th time. But this was taken like almost 10 years ago when she was very small. And it's amazing people can, explore their world, interact with their world, and over time can figure out meaningful patterns in the world that they like and dislike, right? Not only that they can do that, they can actually take their old knowledge and they can adapt it and continue to do that throughout their life. They can actually teach their knowledge to other people, share it, and learn by interaction. So this is my new kid. He's just 3 years old now, and this was when he was just one and trying to learn from her big sister some new things. So this is really amazing that right now is not there in machine learning, and I believe that that's the reason why we the difficulty in training AI system, the huge cost of it, is because we don't have a way to quickly adapt an already trained model to do something new or learn by interacting with the world slowly over time, just like kids and humans do it. So if you actually think about it, why there's unsustainability in training AI systems right now, one major reason for it is that we rely on this kind of stochastic training where we assume that we have access to all the data at all the time. So at least people don't do this in practice completely, but the theory that we rely on for stochastic training requires you to randomly sample a mini batch from a huge pool of data. This is so because we need this, now we need to store all the data in a big data center. We can't just learn from some data source and discard it afterwards, right? So because of this, we need to build big data centers. And because of this, we have to store the whole model in one place and then feed that information incrementally, slowly through randomly sampled mini batches. The question is, can we actually do better? Can we get around this problem? And if you try to look into, let's say this is a very simple example to make you think about why we can actually do better. What I'm showing you here is a simple 2D classification problem where the size of the marker is proportional to how recently this example was picked in the mini batch. Right? So here you see that almost all examples are being touched more or less all the time. So all markers are quite big. And it seems like that picking examples that are very far from the decision boundary they're probably not required after some time, right? But in the stochastic gradient method, there's no such mechanism to kind of make this distinction about what you know and what you do not know. So I really think that this kind of idea is not I mean, there are lots of work on this, but somehow we're not using this, and somehow we cannot get our gradient methods to work well if we start to do this kind of non-random or some kind of bias sampling of the data. So we've been working on this problem with the Bayesian angle, thinking about, because what does the model know, what does it not know, and what does it not need, doesn't need to know. Based on this, we can kind of decide which data examples we should be sampling, and we have been studying this sort of systems under this title of adaptive Bayesian intelligence. Basically, the idea is to use Bayesian principles to come up with a new adaptive intelligence method. So I'll give a very brief summary of it. I don't have much time. So I'll skip through the math and go basically through the methods. Essentially, we split the problem in two parts. First, we want to understand the past of a model. Like, what examples does the model think are essential to it? So this leads to some kind of memory building. And then we use this past knowledge as a prior in a Bayesian setup to boost the future training. And this will be something like memory guidance. So I'll talk about basically the work covered in these two papers on Bayesian learning rule and posterior correction. I'll basically motivate the method through this optimizer in the end that we call POCO optimizer for LLM training. Now, just a warning that when people hear about Bayesian methods, often people are thinking about Bayesian inference. And I just want to warn you that we're not kind of doing any Bayesian neural network or doing uncertainty estimation for them. Our goal is very simple. We want to speed up existing procedures. Maybe they're non-Bayesian procedures for deep learning. We want to speed them up. And essentially, we're taking a Bayesian angle using Bayesian principles to achieve this. We're not really working with Bayesian model and resorting to Bayesian inference. If this sort of theme sounds unfamiliar to you, I'll recommend you to look into my NeurIPS 2019 tutorial on this idea, where I introduce the new way to think about Bayesian principles in the context of deep learning. Essentially, even though you don't have a Bayesian model, you can still actually apply Bayesian principles and view training procedures as running some kind of Bayes rule. So this gives rise to Bayesian learning rule, which is different from Bayes rule. It's an extension of Bayes rule that can be applied to settings where we do not have proper Bayesian models. And I think people really think that Bayesian methods cannot scale to large models. And if you actually embrace this new way of thinking about Bayesian principles, you can kind of make algorithms that have Bayesian flavor to it, but those algorithms scale as well as the existing procedures like Adam. So this is something we did recently in 2024. This is an algorithm called I1. It is an instance of Bayesian learning rule. And what we show is that this algorithm I1, it is as cheap and accurate as Adam. In fact, there is lots of similarity between the two methods. The I1 method is optimizing a Bayesian objective. It's actually the variational objective, also sometimes called variational inference, which Srijit was also talking about. So you have some kind of lower bound that you're optimizing. But what you can see here is that the two algorithms, Adam and I1, are taking almost identical path. And this is because there's a connection between Bayesian ways of thinking and Adam kind of optimizer. One simple way to think about this is that Adam is focusing on finding one model, so like one line or one parameter value theta of the weights. In contrast, Bayesian learning rule or I1 is trying to find a distribution. So it's trying to find the mean and the variance of over the weights. So essentially, you can kind of sample from this Gaussian distribution multiple models and multiple lines, as you see in this plot. Right? So this is the main difference. And I'm not going to go into the mathematics of it because I don't have time. Later on, Thomas is going to talk about this, I think maybe in half an hour. He'll give you more detail. But if you want to think about how we implement Bayesian learning rule, essentially it comes down to taking an existing training procedure and you are modifying it such that you only have to kind of add a little bit of noise, epsilon here, that comes from sampling from the distribution. So there's some kind of very nice thinking about this, which is important to understand the what training examples are important for the model, to understand the past of the model. Essentially, if you think of a classification problem, let's say you have 1D classification problem, and you're trying to separate the circles from the square, you would draw a line in between, right? When you're learning a distribution, essentially it's trying to kind of learn a margin around this classifier. So the variance parameter acts as like trying to fill in this gap that exists between the two classes, right? So this kind of connects back to methods in like SVM that were very popular in the old times. But now if you take a Bayesian angle, we're actually able to bridge those SVM-like method to a neural network now. So essentially, Bayesian learning rule is a more general rule than what I've shown you here. The update looks like Bayes rule, and I'm not going into the detail of this, but essentially the difference is that instead of using the actual loss, the loss that you have here, you are sort of working with the gradient. So for example, if you use an isotropic Gaussian family, then you will use linear surrogates. If you use a full Gaussian family, you'll use quadratic surrogates. And this shows that whenever you assume an exponential family distribution, you are essentially using those kind of surrogates to implement Bayes rule-like updating that also matches stochastic gradient descent and atom-like optimizing. Okay. So I've done this work for many years. This started in 2016, actually, when I first joined in AIP, and I have shown over the years that all sorts of methods in optimization, deep learning, approximate inference, and also global optimization methods are very closely related to this way of thinking about algorithms. Okay. Thomas will give you more detail about how Adam and I1 are related, and he'll also show you lots of results about this. In this talk, my focus is to try to use this idea to reduce the cost of AI training. And the first step, as I said in the beginning of the talk, that we want to build a memory of the relevant past experience. Sorry, this is not very correctly written, but essentially we are trying to figure out what experiences in the past that the model finds important, are relevant and useful. And if we know those experiences, then maybe we can use that to focus in the future only on certain examples, not on the whole data set. Right? And this question actually comes down to a very classical question in machine learning. What does being close to the decision boundary mean? Meaning, what is the similarity measure? What is a representation? And that's what this question is about. There is a lot of work on representation learning, of course. We are taking a slightly different way to think about this. That's actually not disconnected from other ways of doing this. But essentially what we are saying is that if you want to understand data relevance, then you need to think about how much that data example impacts or influences the model. Right? So here in this simple example, I'm showing you that there's a new data. If you add this new data, if the data is very far from the old data, then the change in the model, if you add this data and retrain the model, then the change will be really large, right? And if the data is close to the existing training data points, then the model will not move much, right? So this kind of perturbation is one way to think about relevance. So if you add a more relevant example, the model should change a lot more, right? So in other words, you could say that this is some kind of information gain that you have, and the examples which have more information gain for the model are more relevant to the model. Right? It's a very old idea that has roots in Bayesian methods, but also in robust statistics. Now, our contribution is to show that you can actually estimate this information gain very cheaply. So, essentially, what it comes down to is that because you're estimating a Gaussian here, and this example that I showed you before, the examples that are very far from it, they're less relevant, is what we expect it to be. And what you can do is basically you can look at these surrogates that you get out of this distribution. So here I'm showing you a quadratic surrogate. And what you can do is you can essentially try to plot these surrogates for different data points. So for this blue points, if I look at the surrogate, it's kind of located on the other side. If I take the red point, the surrogate's located on that side. So they're kind of somehow balancing each other. And if I look at the example that is very far, the surrogate is very, very flat. Right? So the curvature and the location of these surrogates is helping us to understand how much they contribute to the model. So based on this, we can actually very cheaply kind of estimate information gain. And this is kind of basically what's some of these ideas are written in this posterior correction paper. You can check out the math there. And it's actually related to the representative theorem that is classic from SVM. It's a kind of extension of it that allows us to apply this to neural network. Okay, so here's an visualization where you can kind of run this kind of I1 algorithm, and you can cheaply kind of derive from there these surrogates. So you don't have to do any extra computation. You just simply read the gradient and the Hessian, and they're already computed in the algorithm, and you can just visualize it, and you can see that examples that are very close to the boundary are kind of somehow are bigger circles that have bigger values for the surrogate. You can run this on real problems. So this is on MNIST, where you see that examples that are very weird looking are probably the ones that the model is unsure about. They are probably close to the decision boundary, and that's why they have high information gain when you try to add or remove or perturb these examples, right? And regular examples are not that bad. So I will skip the rest of this. There's some visualization on that. You can plot these examples, and this will tell you that it represents the class. For example, in this one, it's the traffic light, and the examples on the top are the ones that the classifier finds it to represent this class. Okay. So based on this, we've been working on to use this to kind of figure out what examples are important, and then use them to build a memory and use that memory to guide the training in the future. Without giving you much detail, what exactly essentially comes down in the end is that in this Adam optimizer, you're touching all the examples, you're sampling mini batches from all over the place. But in Poco optimizer, you learn a memory. So you pick out these important examples that are shown in black here. And then you're trying to basically draw your mini batches close to these black points. And so that's kind of is the main idea. And I don't have time to give you the detail, but this mechanism is actually quite general. So it's not only just to boost the training trajectories. You can show that lots of methods in continual learning, unlearning, influence functions, student-teacher learning, model merging, federated learning, they're all kind of doing the same very mechanism. So it's a kind of a Bayesian mechanism to adapt the knowledge that you have from the past to do something in the future. In the current work with this POCO optimizer, we are using a very specific version of this where we build the memory in an outer loop and build a memory buffer. As I showed you before, you look at the surrogates, you pick those from that, and then you build kind of a posterior. So I don't have time to give you detail, but essentially you build a posterior using the Bayesian learning rules, and then you use that posterior to boost the future mini-batch iterations inside. So in the end, you don't implement with Bayesian learning rules, you implement with something like I1 or something like a perturbed version of SGD. So these are very easy to implement. But essentially, this leads us to, allows us to very easily implement these ideas for a very large model. So I want to just finish the talk by showing you an example. So this is what I showed you before, that I1 and Adam, they look very, very similar to each other. But what we actually show is that if you do this posterior correction, this POCO optimizer, if you apply it, let's say certain instance, you start to do this kind of correction by using the memory of the past, you get a sudden jump in the performance. So this is quite, it's quite encouraging. Of course, I'm hiding a lot of details here, so it doesn't really mean that the cost is reduced in this case. And we're working on right now how to reduce the cost, but there's a lot of promise that this approach has in reducing the cost that we are still exploring. Okay, so I'll finish the talk with this. Essentially, I showed you 2 points: understanding the past using Bayesian learning rules, so building the memory, and then using it to boost the future by using this memory and then doing this kind of double loop algorithm where you build some consolidate old knowledge in a posterior and then use that to correct the future training. Okay, so yeah, I'll just thank my collaborators and finish the talk. Thank you.
Thanks for the wonderful talk. Any questions from audience? There's a question in the chat box. Can you see empty?
Mm-hmm. Yeah. So the question is, what is the analog of decision boundary for tasks beyond classification, such in language modeling and generative modeling? Yeah, thanks a lot. Yeah, this is an important point, actually. So I'm actually saying decision boundary here because it's easier to understand. But if you would notice that so here there's a decision boundary, but if you notice that when I'm talking about information gain and relevance, I'm not thinking about decision boundary. So in general, you can always think about information gain. Like if you have an example, if you add that example to your model changes a lot. And that's how we are actually deciding whether that example is relevant or not. In the classification case, you can visualize it with respect to the decision boundary, so it becomes very intuitive. But in general, we're not actually thinking in terms of decision boundary. So, as you said, there is no analog of this.
Any other questions?
So when it says, so the question, a follow-up question, when it says the model changed a lot, does it mean the model output changes a lot for all inputs? Yeah, so that's one thing that changes in it. So if you really want to understand it completely, what you should be doing is you should be looking into the KL divergence between the posterior you had before and the posterior you have after. And if you did a very simple approximation of it, it may come out to be changes in the prediction If you go in the paper, you will see I talk about this, that prediction mismatch is one way to measure information gain. That's the simplest way to do it. But then there's also more, if you change the posterior approximation, use better posteriors, then come out to be gradient mismatch or Hessian mismatch. So as you increase the flexibility of the posterior, you get better and better notions of information gain. If any other questions you have, I'm happy to answer.
In terms of computational time, is there some disadvantage this can bring, or?
No, I don't think so. I mean, you can actually apply this to, so the issue, like why the Bayesian angle is important is because like what it actually shows that if you, like as the previous question I was telling you, right? So the predictions are embedded inside the gradient, and then gradient is slightly more informative than the predictions, and Hessians add another dimension to it, right? So it's getting more and more complex. So if you want better estimate, you may want to use better surrogates, right? But right now we cannot afford anything more than doing gradient-based methods. So we'll have to work with this, right? So that's kind of what it comes down to.
Okay, thanks again, MT. Maybe it's time to move on to the next talk.
Thank you for the introduction, and it's nice to be presenting again to this audience. So the title for my talk is Formal Concept-Based Models. It's a slightly different genre of work, I would say, but I'd love to present and get some feedback too. I'm currently associated with IIT Hyderabad and Microsoft Research too at this point. Over the last many years, our research at IIT Hyderabad has focused on one core thesis, which is on how do you build robust and reliable machine learning models in evolving environments. So we have worked a reasonable bit on making these models trustworthy and explainable, making them more robust from different perspectives, making them evolve with time, continual learning, open set learning, so on and so forth. And also, how do you make them work in data and label deficient settings such as zero shot, few shot, domain generalization, so on and so forth. More recently, we have been expanding to more contemporary architectures in terms of multimodal LLMs. How do you make them more reliable and robust? Looking at grounded spatial reasoning, verifiable reasoning, semantic tokenization, visual agents for fine-grained actions, and so on. But a core question that we've been trying to explore through all our efforts over the last few years is, are we fundamentally learning right? So let me try to bring that provocative thought in the next slide here. Is if we had to go through a thought experiment, a toy example, is for a large part, the way supervised learning works at this point in time is through learning via prediction, right? So you obviously have your data labels, you have a machine learning model that you learn through different algorithms, so on and so forth. But if one had to take a step back and ask the question, what if we taught kids the same way, right? MT just talked about the Bayesian approach to learning, how probably getting inspired by how humans learn. Now imagine we had the same supervised learning paradigm for teaching kids. The way we would teach 2 plus 2 would be to give 4 different options. Maybe that'll expand to 100, 1,000, million, and so on. And the kids would be asked to choose one among those options. And this is how we learn to this day when we do learning via prediction, right? Obviously, that this doesn't seem the right way to fundamentally learn itself. So what could be the alternative way of learning is something that we've been exploring, is to go from learning via prediction to learning via reasoning, right? And what does this mean? This is just one take at it. I wouldn't say this is the only take at it. The one take that we have been exploring is, if you had an image of a cat and a machine learning model called it a cat, can we instead move to something more nuanced than this? Is, given a cat, can we first understand the beady eyes, the whiskers there, the 4 legs, the pointy ears, the furry coat, and then the machine learning model puts this information together to say it's a cat because it has whiskers, 4 legs, a furry coat, pointy ears, and beady eyes. This is, as I said, one take at saying how you can achieve learning via reasoning, at least something that we've been working on over the last few years. One can say that the concurrent work on aligning reasoning traces in LLMs could be like a naive effort in this direction. I personally believe that one can be deeper than that, that can be looked at as one approach to doing something like this. So the overall idea that we are envisioning in this direction is, suppose you had a bunch of transformer blocks that made an LLM. Can we get human understandable semantics at intermediate levels, right? So you could look at it as like a verbose mode of an LLM, which speaks out what it realizes at different levels of processing. And now, can you also have logic modules where these concepts, you could read them as symbols, can be differentiable and integrated inside a neural network to compose these concepts meaningfully, not just through and or operations, but through maybe other kinds of differentiable logic operations too, something that we have done more recently also. And then how do you bring these responses together in a more reason around these concepts and put these logic operations together and then reason out your response, right? So you could also look at this process as having a loose inductive bias during model training that favors human understanding, right? So I think one of the premises of this approach is that we want models to be understood by humans, right? So after all, humans have created these models. That's the fundamental premise of this approach itself. So one of our earliest works in this direction a few years ago was a very, very simple, naive approach, which was like we took a lot of my examples of from computer vision, by the way, because that's the where I've worked a lot, but I think the core ideas are relevant to other domains too. So you'd have a backbone network, a CNN for a way to bring in concepts as an other pathway, which is used to predict the same class label, right? So we have an overall architecture for this, which has reconstruction laws through these concepts, fidelity laws that checks whether the outcomes here correspond to the outcome that you would have predicted directly, and also your standard classification laws. Since then, we did a bunch of other things, but more recently, last year, we came up with a method where you could do something like this for transformers too, right? So where given a transformer block, given your standard input tokens and some concept tokens that we embed as vector embeddings, we have some loss terms that take intermediate output tokens of a transformer block and align them using a concept grounding loss with some concept loss. And we finally also have a classification layer that matches these concept embeddings with label embeddings. And that's how you can extend this to perform classification tasks or even other kinds of tasks. More recently, earlier this year, we also extended this to incorporating differentiable logic inside these kinds of concept inferences. So for example, if you had a certain layer of a neural network to be a bunch of meaningful concepts, such as say furry, friendly, big, whiskers, so on and so forth, how do you then have differentiable logic operations? Could be a knot of friendly, could be a XOR of big and small, so on and so forth. How do you do this is something that we achieve through what we call as a logic module, where we use fuzzy logic to be able to make this differentiable. And now this entire logic module, along with the rest of your network, becomes end-to-end backprobable in a standard way, right? So we call these logic CBMs. So these are some past work that we have done, but for the remainder of about 15 minutes of my talk, 14 to 15 minutes of my talk, I'll talk about some recent work that we have done where we have extended these directions of works to capture hierarchical semantics within neural network models, right? So just to clarify, concept-based models, we are not the only ones working on them. There is a reasonable amount of literature, largely from around 2018, where people have tried to embed these kinds of concept models to get better interpretability. But we are also looking at that as a more natural paradigm to learn, right? So once again, going back to what MT mentioned, I think a lot of human learning goes around how we learn concepts and how we also interrelate concepts between different tasks, right? So in some sense, this is an effort in that direction. So one of our observations in this work, so the rest of my talk is going to be about one specific work. I'm just giving you the context so far. So in this particular work, which we call as formal concept-based models, and that's the title for this talk, our objective is to capture hierarchical semantics within neural networks. And the observation we make is that existing concept-based models largely learn concepts at a single layer, typically the last layer, right? So you learn whatever you have through earlier layers of a neural network, and the last layer, you have a bunch of embeddings, and then you associate them with concepts. And then you have a simple linear model that takes you to your final class labels. That's the way typically it's been done over the last few years. So the concepts are learned at a single layer. It's typically treated as a flat, unstructured set, ignores any hierarchy or structure in the semantic concepts, and it doesn't really align with the depth of a neural network by itself. Right? On the other hand, we know that human cognition often organizes concepts hierarchically. We generally have a progression of general concepts to specific concepts, and there are different levels of abstraction in our own understanding of the world. Right? An example could be like you have an animal and vertebrate to be a general concept, and an animal vertebrate feline would become more specific than that, and then you have animal vertebrate feline sharp teeth to be a bit more specific than that, and so on and so forth. So the question that we try to ask here is, how do you bridge this gap by learning concepts across network depth? Rather, how do you align a neural network's depth-wise representations with some kind of semantic hierarchy, so to speak? So the key insight that we get here is that, very well known, but probably our contribution is how we formalize this rather, is more classes share general attributes, fewer classes share more specific attributes, right? So if you had animal and vertebrate, that's probably shared by a bunch of different classes, dog, cat, and tiger. But if you said animal, vertebrate, and feline, then it's shared only by cat and tiger. Right? So very simple observation. So which means this subset superset structure creates a very natural hierarchy, more general being animal vertebrate, and all the way to specific being sharp teeth, purrs, and so on and so forth. And one of the tools that we end up using to achieve our objective is a tool called formal concept analysis, which is a mathematical framework which we leverage to extract such a hierarchy. So formal concept analysis is a mathematical theory largely used in data analysis. It has roots in category theory. It formalizes the notion of a concept. It defines what is called as a formal context as GMI. G is the set of objects or classes, what we would say in machine learning. M is set of attributes, and I are binary incidences, relations between them. Right? So it would form a matrix such as this, where a cat and attribute have an incidence relationship. So what formal concept analysis the theory gives is a structure for A and B, where A comes from the set of classes or objects, B comes from the set of attributes, and then it introduces this notion of up arrow and down arrow that comes from the formal concept analysis literature, where A is defined as the objects shared by all attributes in B, and B arrow denotes all the attributes shared by objects in A. And it's interesting to note that this structure, formal concept structure, forms a partial order over the relation less than or equal to. So let's go further on this. So the set of such formal concepts forms a lattice, right? Once again, this comes from the formal concept analysis literature, which is a kind of a partially ordered set or a poset. Right? So you have this formal concept, which is more abstract at the top, and then you have a formal concept that's more specific at the bottom. Right? An example of a lattice would look somewhat like this, where if you gave the attributes root and fiber rich, you have some objects or classes, beetroot, radish, carrot, and then as you become more specific with your attributes, the space of classes starts shrinking. Right? So all of this is what you have in the formal concept analysis literature. So what we do in this work is try to see how do you bring this into the training of a neural network itself. So the first thing that we do is to construct a lattice in common data sets that we use with training neural networks. So what we have as an input is a class attribute incidence matrix, typically a binary relation, which attributes are presented in which class. And this structure is also sparse by design. Often the fill ratio is less than 0.1. And just as examples of datasets that we work with, AWA2, CIFAR100, and ImageNet, these are the kind of classes and attributes that we have. So we use the formal concept analysis literature to construct a hierarchical lattice, which gives a set of formal concepts, which satisfies a partial order relationship. So there are multiple levels of semantic granularity. And just to let you know that this is feasible, the construction time for building such lattices from classes and attributes is fairly quick and it's a single offline step, right? So ImageNet 100 takes about 4 seconds, AWT takes about 37 because it's more dense in terms of the relationships, and CIFAR 100 takes 2 seconds and so on. And the output of this step for us is an attribute set, which is typically called intent in the formal concept analysis literature, and an extent or the class group set at every level of the lattice. So our core idea is to see how do we use these as supervision signals to train a neural network in practice. So our idea is fairly simple, and we believe that simple ideas translate to working at scale. So the idea here is how do you use the information from the lattice to produce intermediate semantics? So we plug in attribute and classification layers at intermediate positions of a neural network to use this information. A lot of our experiments are run on ResNets, more for just being pliable within academic settings. But the idea here can be used with transform blocks too, and we also have some results with vision transformers and so on. So the idea is if you broke down your network into different blocks, be it transformer or residual network blocks, the understanding is that as a network learns, there are attributes that the network learns at earlier blocks that correspond to more general attributes. Right? For example, you could have the output of block 2 to have attributes like big, wrinkled skin, gray, so on and so forth. This already happens in practice perhaps, but often there's no semantics that's tapped out of it or supervised at this point in time to learn such a network. Right? So this is what we try to leverage in this work. And that's the role of the formal concept analysis lattice here. So this is how a lattice looks. C denotes the classes, A denotes the attributes, and they're used to train this network at different intermediate positions. So the obvious question that comes out is for a certain class. So the intuition here is general attributes learned earlier cannot help differentiate between all classes, but they can help differentiate between certain groups of classes. That's what we try to leverage. So the question becomes for a certain class I, what is its ground truth group at a certain layer? And for this, we use the lattice level. We use some heuristics here to get some class cluster densities and to be of the representations that you get at different blocks, and then decide which lattice level you want to use for supervision at different blocks of the neural network itself here. Right? And you combine all of the attributes that you have at a particular layer of a lattice. So we do a union of all intents at that particular level, and that is used to now supervise the attributes that come out of the representations at a particular block. So our overall loss function uses binary cross entropy at different intermediate layers. And the reason we do binary cross entropy is that at a particular layer, there could be multiple classes that could be active. And to be able to enable all of them to be active, we use binary cross entropy at intermediate layers and your standard cross entropy at your final layer. And this can be in addition to anything else that you do, right? So this is not like the only loss that you use. So if you're using any other regularizer, any other loss, that can also be added to the setting in practice. So that's the simple implementation approach. Just to summarize what we do here. So the lattice is done as an offline one-time step, and at each from an architecture perspective, we have a concept encoder at selected blocks and a classifier that comes out of the concept encoder that is used to classify at each intermediate block, and that's only used at the intermediate layer. So just to let you know how this works, so you extract features at selected network blocks, we do global average pooling, send it the attributes through a concept encoder, use binary cross entropy loss, also have a binary cross entropy loss on predicting the class labels themselves, and then you have an iterative refinement where the softmax of or the logit of that particular class is progressively used in later layers while selecting that particular class. So which means if a class was lesser likely to be found in an earlier layer, it has a multiplicative impact on the later layers while selecting a particular class. And then the final layer uses standard cross entropy. So we also theoretically analyze this work. And firstly, we have a couple of theorems. One is we show that there is an order consistency here. That is our approach called FOCA CBMs, preserves semantic ordering in the representations that you get with high probability. The interpretation is that the lattice structure provides an inductive bias towards an hierarchically consistent solutions, hierarchically semantically consistent solutions. And the second one is an information theoretic benefit, where we show that supervising using a formal concept analysis guarantees information gain between those blocks of layers where you bring in supervision. And the interpretation here is that the formality property that we use ensures that each attribute set is informationally complete, as I will show a couple of slides down. The key insight here is the random concept hierarchies lack these guarantees, but the formality property is crucial for such optimal supervision. Here are the results that we have. We compare our approach against a bunch of different concept-based approaches, all of which induce concepts of supervision at the end. And we do it across ImageNet, AWA2 and CIFAR 100. We have test accuracy. We also have a Gini index to find out how good the representations are at intermediate layers. So this is the mean Gini index across multiple blocks. We also have the David-Bolden index to get the class compactness at different intermediate blocks. Once again, the mean of several blocks is shown here, and our method outperforms existing methods. Just to give a better visualization, we also do TSNE visualizations of our representations at different blocks. So one thing that you see here, the inverted green arrow and the cross are our methods here. And you see that we get a lower DBI and a lower impurity, which is what is desired, at earlier blocks than many other competing methods. And we get the lowest impurities and DBI as we go to later blocks. We also notice that through our approach, classes are better separated earlier than later, as you can see when you go from left to right, from block 1 to block 4. On top is a standard CBM, and on the bottom is a FOCA CBM, which is our approach. One of the benefits of such concept-based models is also test time interventions. People often use them as a way of as a method for the user to interact with such a model and check whether meaningful concept-class relations have been learned. It's a standard approach where you typically take a concept layer and intervene on one of the concepts and see how the outcome changes, and that tells you how good the concept-class relationships were learned in the model. And what we show using our approach is one can do multi-level interventions, right? In fact, we go on to show in our approach that if you intervened earlier, right, you actually get much better benefits because you're intervening at a more general attribute level, which has a better downstream impact on the model's performance on the final classification, rather than intervene only in the last layer, as is done typically with standard concept-based models. Right? So that's the same thing that's shown here. The main takeaway from this visual here is for this particular class of sea snake, the intermediate layers have more general attributes that allow you to intervene better, rather than the last layer, which typically has a class label like a bug or so on and so forth, and where the intervention may not significantly change the outcome itself. So we also do a comparison. Do you really need a formal concept lattice, or can you get a concept hierarchy from an LLM and be able to use it? Our framework allows both. So you could also use an LLM-based hierarchy directly to supervise our approach in our code as such. But what we notice is that if you turn off 1% of attributes, which is typically called a concept leakage test in concept-based literature, we show that using our approach leads to a 30 to 40% accuracy gap, which tells that the concepts are very tightly used in our approach. Whereas if you use an LLM-based hierarchy, there's less than 5% accuracy drop. So it suggests to us that our formality property that we use in the construction of the lattice matters a lot, and a lattice created using such an approach is more informationally complete than just using an LLM-based hierarchy. We've also tested this on VIT backbones and show improvement even in those kind of settings. And from a computational efficiency perspective, this is not costly at all, because the lattice construction is a single offline step. It doesn't change the training step per se, and that makes this approach scalable as much as any other network is scalable in practice. Some of our ongoing and future work is extending this to vision transform and foundation models, this multimodal features and autoregressive settings. We are also looking at weakly supervised hierarchy construction and also dynamic concept adaptation in practice itself. As I said, just to circle back and complete what I started with, this is one approach to learning via reasoning. I wouldn't say this is the only approach to doing learning via reasoning. We are just trying to give it our best attempt to train models that can inherently learn better rather than learn via prediction. And this approach was on using concept-based approaches to do it. And I believe that such concept-based approaches are placeholders for symbolic methods in connections architectures. I'll stop there. This joint work with the entire Focus CBM work was joint work with Deepika, Sayanta, Ankit, and Krishna Vishwas, who's on the call, and they'll probably answer better on this work. Also acknowledging all our students, alumni, collaborators, and colleagues, and happy to take questions. Thank you again.
Thanks for the great talk. Are there any questions from audience?
So may I ask an elementary question?
Yeah.
So in earlier slides, you approximated the logical computation in a continuous way so that neural network can be trained. So would you explain that part again? Did you just continuously approximate the logical computation?
Correct. It's a NeurIPS 22 paper called Deep Differentiable Logic Networks. Where they do is they take any logic operation and approximate with the corresponding fuzzy logic operation. And because of the T norms that are associated with fuzzy logic operations, you can write out most of your, I don't have the slides here, unfortunately, that was a different paper. I'll be happy to share it separately. So because of the T-norm property, all of these logic operations can be approximated using arithmetic operations, which are backprobable. So that's how you get it. So it comes from a paper.
Is it similar to the converting a combinatorial optimization into a continuous optimization problem?
You could say so. Yeah, I don't think that our work or their work exactly formalizes it that way, because this is a standard trick people use. It has been used in formal verification way back in the 90s. It's not a new topic in general, but in machine learning probably not as used as much. But as I said, the NeurIPS 22 paper called Deep Differentiable Logic Networks is the paper that introduced it, and they don't do it with concepts though. They just try to do the entire network as what they call as logic neurons. We try to use it on top of more symbolic concepts which can be combined using logic operations. But
Yeah, thank you very much. Yeah.
May I ask another question also? So yeah, thanks for the great talk. It's very interesting, these concept-based methods. And I was wondering if there are any potential limitations to your work and other concept-based models. For instance, I was wondering if the attributes, you have to fix them in advance.
Absolutely. So as with anything, whenever you're trying to optimize more than one performance criterion, there's always a trade-off. So here we are trying to get good accuracy as well as good robustness and reasoning or interpretability capability. So there's always that trade-off when you go for more than one objective criteria. But the benefits are that you get inherently more robust architectures, architectures that can give you reasoning traces and so on and so forth. That's the benefit. So there's definitely a trade-off. You're not going to get the best accuracy using this kind of an approach rather than if you used your standard non-interpretable approaches. Sorry, what was your second question?
I was just saying, like, it seems the attributes need to be fixed in advance, right?
Correct.
Class list and also the attribute.
Very much. Yes. Yeah. Yes. So that is right at this point in time. We do rely on constructing that lattice, but these days many others do it too. I mean, it's one of the things we are studying at this point is what if the lattice is noisy, either at training or at test time. I mean, what if you want to do something beyond? I think it's possible to do it because you have language embeddings these days. So you can approximate a particular concept using all concepts in its vicinity, so on and so forth. So I think you have some tools to be able to do it in a bit more robust way. But you're right that that's a limitation of this work at this time.
Okay.
Okay, there's a question in the chat box. Vineeth, can you see it?
Yes, Deepak asks, it's highly likely that if you visualize the intermediate layers, GradCam-like maps in FOCA, it should better ground in images than vanilla models. Yes, we did study this too, and that's what, not in this work. We had an earlier work, I talked about grounding concepts in transformers. That was at IIIT 25. We did study this in detail, and we actually found that when you ground concepts, when you learn, localization comes for free. Right? So what I mean by localization is we don't have any additional loss to say that an attribute must be localized in a part of an image, but it automatically happens as part of the network. That's a good point, and that's something that we observe in this work too.
Okay, due to time limit, thank you again, Vineeth.
Thank you.
Yeah, thank you for the invitation, and happy to present my work here. I will talk about variational Bayesian methods applied to large neural networks. has been ongoing work over the last years, and this is like an overview talk over the results that we've got. To motivate variational training, I have here a very simple example for a prompt that we gave to a llama model. Alice eats cereal for breakfast 4 days a week and pancake 3 days a week. And then the question is, this morning Alice had A, cereal, or B, pancake for breakfast. And the answer is, and if the model was fine-tuned with Adam, it was very, very confident that Alice had cereal for breakfast. So the probability, softmax probability of the next token for the token A was almost 100%. And with our variational training methods, the probability was much more balanced between A and B. So this is typically a reason why people were initially excited about Bayesian methods in deep learning, that in underspecified situations or in situations where the data does not fully describe my answer, that the uncertainty is taken into consideration. But in this talk today, I want to give also a much more nuanced angle that variational Bayes, okay, this is a cool application. You can get better predictive uncertainty, but there's many, many other benefits why you should do variational training. So there's regularization benefits, it helps for model merging, fine-tuning, federated learning, and so on. So I hope to give some broader examples. And yeah, typically people say, oh, these variational methods, they look all very principled, but they don't scale to large neural networks, or they're very difficult to use. And yeah, this is just not true. So in our paper in 2024, we introduced an optimizer that, if you attended Emtiyaz's talk, he already mentioned it. It's called Improved Variational Online Newton Method, IVON. And it's very easy to use. You just install the Python package. You change one line of code, you comment out your Adam optimizer, you comment in IVON, and you have to add one extra line to your training loop, and then you can have the variational Bayesian training of large neural nets, and there is almost no overhead. So here we trained a GPT-2 model up to almost 1 billion parameters, and you can see after 24 hours of training, the IVON is not much behind the Adam training. And the final solution, the larger the models get, the better, or the larger the gap to Adam also gets. So you get this regularization benefit that in especially large models on little data, we found that this method works really, really well. So yeah, this is our work. You can do this variational training very easily nowadays, and I hope you will try it out. To give you kind of a main overview, what's the difference between Adam and variational training? So the main difference is, in Adam, you learn a single parameter. So in your neural network, for every connection strength, you have a single parameter, and this is what your optimizer learns. And in this variational Bayesian training, for every connection in the neural network, you actually have a little Gaussian distribution that has a mean and a variance. And then you're learning both of these parameters. And this leads to very noisy dynamic weights, as you can see here in the visualization, where the Adam solution gets very, very confident that the decision boundary must be here, especially also in regions where there's no data at all. You're extremely confident, oh, it must be like this. And with the variational training, there's an inherent uncertainty. You can see all these little gray lines here in the animation. These are random models sampled from this distribution here, and they all give plausible explanations of the data. Also in regions where there is no data, you can see that there's multiple possible explanations. So this is automatically what you get for free if you do this one change of code. You replace Adam with IVON, and suddenly you get this distribution, which gives you this uncertainty in regions where there's little data and gives you these very noisy dynamic weights. And it's also among the most accurate methods. I will not go so much into detail here, but there was a NeurIPS challenge on Bayesian deep learning, where the goal was to approximate the exact posterior distribution using approximate methods. And with our method, we won the first place in this competition. So it outperformed all other Bayesian methods that were around at that time. So it's not only easy to use, but it's also among the most accurate methods. So, okay, what is this method doing more on a mathematical level? And so what is actually variational training? Typically in deep learning, you minimize your loss function and perhaps an L2 regularizer over your model parameters theta. And in the variational approach, we actually make only a little change. You only add on top what is in red. We search for a distribution. We say if we sample from that distribution, still our loss that we like and used before should be low. And we have an additional regularization term that forces these models to be diverse. And we prefer also to rewrite it in this way, that you can write the regularizer and the entropy as a KL divergence of that distribution that you're searching for to some distribution P, some reference distribution. And yeah, there's these two terms, and that reference distribution is just e to the minus regularizer. So yeah, that's the idea. We collect multiple diverse solutions within our probability distribution. And yeah, these models, they should all be experts. So if I sample random weights from my variationally trained LLM, they all should have low loss, but they should also be diverse. So one of them is maybe an expert in math, and the other one is an expert in a certain language and so on. So we want all of them to have low loss, but also have some diversity. And having this distribution available is very useful for various downstream applications. I will go into some of these in the remainder of the talk. Then how are we able to do this? How can we scale these methods to large neural networks? So here again, I wrote the objective that we are now minimizing. And our method, this Ivan method, it actually takes a very similar form to the Adam or RMS prop optimizer. So an RMS prop, you would just minimize this L of theta or an Adam. And you can only do very small modifications to that method, which are highlighted here in red. And then you're optimizing these additional red terms, this KL regularizer plus the expected loss. So the main difference is that we now during training sample from that distribution that we are optimizing over. So this is our Q of theta, and evaluate the gradient at the sample point. We don't use a squared gradient, but instead something that looks like this. So this is actually an unbiased estimator of the diagonal Hessian. That's why we call this a Newton method. So this is actually much closer to Newton method than Adam, which uses a squared gradient. Line 3 is exactly the same. And line 4, we divide by h rather than square root of h, because we now use the Hessian matrix. So in a Newton method, you would divide by the Hessian. And this line is actually not a computation. This is just based on h and this weighting parameter, inverse temperature parameter that we have, how we get this posterior uncertainty just from this Hessian accumulator that we run. So as you can see, because it tracks the same quantities as Adam, there's absolutely no memory overhead. And there's only a little bit of computational overhead, which is due to the sampling of the random numbers. And this optimizer, if you modify your Adam code to include these steps, or if you use our package, then you're optimizing this objective here. And in this way, we were able to scale these methods to large problems such as GPT. And yeah, maybe for people who are more interested in the math, this method actually comes out of a very principled natural gradient descent on this objective here, which is in this Bayesian learning rule paper. Yeah, recently we applied this to fine-tuning Llama 2 models, and on small data sets here, these are small reasoning data sets. We have here these two works out, variational low-rank adaptation using Ivan and improving LoRa with variational learning. So this is a LoRa fine-tuning, and we got huge improvements in accuracy, especially because these are small data sets. These standard optimizers tend to overfit and get overconfident, and we could get up to 6% improvement over Adam on these reasoning data sets. And looking at quantities like calibration error, so this is the overconfidence or underconfidence in your answer. Calibration error is also greatly reduced compared to the Adam model. And it actually turns out if the more compute you put into this method, the better it gets. So it scales very well with compute. So if we train longer, the accuracy keeps increasing for the Ivan method. Whereas for Adam, the accuracy actually slightly decreases if you train too long. So this is some kind of implicit bias in the optimization towards low complexity solution. Some people would call it grokking, that the longer you train, the better explanations of the data are found and your accuracy goes up. So this scales very well with training compute. So in the future, we expect these methods to gain much more significance as compute just keeps increasing, and maybe at some point we don't have that much data in it. It's also very data efficient. So especially on small data sets, the gap to Adam is large. As the data set size increases, the gap decreases, but is still significant. We can trade off between accuracy and calibration using that variational posterior that we optimize. So we can just predict at the mean of that posterior distribution, and we get very high accuracy, but we can also do sampling, draw like multiple models and average their predictions. And as we increase the temperature of that sampling, the accuracy actually goes up slightly a bit, and the calibration error just keeps going down. So we can trade off accuracy and calibration very easily with this method. And this trade-off curve, it strictly dominates other Bayesian methods. So this was based by backpropagation-based LoRa method from NeurIPS last year. These are Laplace approximations, and they are all strictly below what you can get with this Ivan optimizer. And additionally, if one prunes weights which have very high variance, the solution can be slightly improved further. The Ivan training is also very useful in LLM decoding. So let's say you've trained your LLM using this variational method. What can you do with it? The most straightforward thing is if we generate responses from the language model, we can use that posterior to improve the quality of the responses. And the simple approach is typically something that people call beam search, where you sample from the softmax in the last layer and combine multiple samples to give a better answer. But what we do here is we first sample from this posterior distribution over the weight. So we look at these different experts that we've collected all in our probability distribution. And then we sample from we use the softmax probability and combine all of these models during inference to improve the decoding of the model. And using a single model during decoding, where we just sample from the softmax probabilities multiple times, we can get, for example, for machine translation, a score of 19.7. And additionally, sampling models from this posterior during decoding, the machine translation score goes up almost by or even over 1 point. So this is a very significant improvement. A human would rate this machine translation to be much better than this machine translation. So this Q of theta that you get for free with the Ivan optimizer is very useful to just improve the quality of the language model during decoding. And this scales also very well with test time compute. So the more samples we generate from that posterior during decoding, the better the answers get. And of course, you can do the same for Adam, where you just sample from the softmax, but it degenerates or it saturates at around 72%, 73%. The accuracy saturates, whereas sampling from the posterior, the performance just keeps increasing the more samples you use during decoding. So this also not only scales well with more training compute, but it also scales well with more test time compute. Yeah, this is another work where I was actually not involved, but a group from TU Darmstadt in Germany, they used this Ivan optimizer to train large multimodal models. So they trained a language vision model using Ivan. And then they studied this question answering system. For example, does the pedestrian light say walk? And here the correct answer is no, but the Adam trained model is highly confident that it's yes, whereas the Ivan trained model, due to sampling from this posterior distribution that we get, the it's much more uncertainty aware, and one can actually abstain from answering and say, okay, I actually don't know what this says. And also in other situations where the Adam model is actually not very confident, and this is a dog, but it's clearly a dog, the I1 model can be confident. So the sampling does not only just smooth my predictions, like some naive temperature scaling, but it can also actually sharpen your predictions in situations that are correct. So it just improves your quality. Then, of course, the question is, why does all of this work so well? And one explanation is that the solution found by I1 is very different than the solution found by maximum likelihood or MAP training. So this is a very simple loss landscape here, where white is high loss, gray is low loss, and okay, the minimum is here, but if you train with I1, you don't go to the minimum, you go to a very flat region where you have many solutions around your solution that have low loss. And these are called flat minima or flat regions. And it's known since a long time that if you do this variational training, then you're actually minimizing for low description length solutions, which coincide with these flat minima. And there's a lot of theory that these flat minima have many desirable properties and correlate with better generalization. So the method searches for flat minima. And we had a paper at NeurIPS last year where we had also a proof that I1 finds flatter minima in a regime called edge of stability. So if you train with gradient descent, your sharpness of the solution, this is the largest eigenvalue of the Hessian, is around 2 over rho, where rho is the learning rate. So I want to train with large learning rate to go to flat minima, and then my gradient descent hovers around this 2 over rho. And I1, depending on the posterior variance that we set, goes to a much flatter solution with lower sharpness. And the question is there a similar quantity like 2 over rho that can characterize the sharpness of I1 solution? And we developed here a theory that can predict quite closely the flatness of the solutions. So this is based on an analysis on a quadratic function, where the intuition is that due to this noise injection in I1, you're actually unstable, and this helps you to escape from sharp minima. So if your quadratic is too sharp and your posterior is too noisy, you will basically bounce out of that sharp quadratic and then settle into a flatter one. And the summary here is that for gradient descent, we get a decrease in loss if my sharpness is less than 2 over rho. For I1, we get this expected decrease in loss if my sharpness is again here by the learning rate, 2 over rho. So we should still use a large learning rate, but we get this additional variational factor, which depends on the posterior variance, the number of Monte Carlo samples, and some constants. So we can here have a proof which characterizes that our solutions are always below 2 over rho because this variational factor quantity, we show that it's less than 1. So this gives a proof why we see these good results. And yeah, as a last point, I'm almost out of time, but I would like to also talk about a recent work that we will present at ICLR this year, next month, on federated learning, where we improved the ADMM methods, a very fundamental method from the 70s that has been used a lot in federated learning. For example, this FedDyn method uses it. It's basically, it sends this, we have a central server which stores a global parameter, it sends the parameter to the client. The clients do local training and send back their own parameter and their gradient. This is roughly some kind of ADMM strategy. And we generalize this to a Bayesian setting where we send the distribution from the server to the client, and the client send back their locally trained distributions trained with I1 along with gradients in distribution space. And the method here that implements this Bayesian ADMM with I1 to this local training is here shown in red, and it gives large improvements over the regular training with regular federated learning methods. And since there's no overhead, there's also no change in runtime. And yeah, why does this work better here in federated settings? So there's many reasons, but here's one intuitive illustration. This is the last slide. So with federated ADMM, if a client or general federated learning methods, if a client has an outlier, then it might still overfit quite a lot on that single outlier and be very sure that my decision boundary must be here. Whereas if you train with I1 locally on your client, you maintain this uncertainty shown here in the dashed line, and you're much more suspicious of the outlier. And because you maintain this uncertainty, when the data from the server and the other clients comes in, you're able to adapt in a single iteration to the correct solution that's specified by the other clients here. Whereas with federated learning, because it was so overconfident that the decision boundary must be here, it took five communication rounds to kind of recover from this mistake. So the summary is that this uncertainty that you maintain here allows you to recover much more quickly from mistakes, or don't make mistakes in the first place. And this explains here why we can get such large improvements in these federated learning. So that is all. Thank you very much.
Thank you for the great talk. Okay, is there a question in chat box? Thomas?
Okay, there's actually 3 questions. Okay, the first one is about having to invert a Fisher information matrix. Yes, so it appears it's expensive, but we actually can get around this because this inverse can be just a gradient in a dual coordinate system. So this is written in this Bayesian learning rule paper. So in practice, you don't implement it like this, but you really implement it like it's shown in line 1 to 5. You can see in line 1 to 5, you never need to invert any Fisher. But implicitly, by doing lines 1 to 5, you're inverting it. The compute requirement was exactly the same as the Adam training. It was trained on exactly the same hardware and took almost the same time. What exactly is the utility function used in the LLM decoding? We tried multiple utility functions. So if you use a 0-1 utility, you recover the beam search. And I think it was some kind of so this was done by Nico Daheim here. So if it might be better to check the paper and ask him. But on top of my mind, it was some kind of added distance or some kind of utility function like this. And the third questions are the flat solution over the space of parameters or the space of inputs. So the flatness is over the space of parameters. So here this is for a very simple model which only has 2 parameters. And the flatness is in the parameter space. And intuitively, you get flatness due to the noise injection here. You add a little bit of noise to your parameters, and then it has to have low loss basically for all of these. You're optimizing to have low loss for all of these noisy weights, and then if you're in a flat place, you can achieve this.
Hi, Thomas. Thank you for the nice talk. Can you hear me?
Yes.
So I was wondering if there are some benchmark datasets to check the uncertainty modeling capabilities of LLMs.
Benchmark datasets to check the uncertainty quality of LLMs. I mean, this is typically used in the kind of Bayesian LoRa literature. Are these just fine-tuning datasets and looking at things like calibration error or test loss?
Like for instance, how well they are able to deal with out of distribution data.
I know of a survey also written here by my co-author Nico. He wrote a survey on uncertainty in LLMs, uncertainty evaluation in LLMs. So probably in that survey. But personally, because we care more about these downstream applications, so we're actually not working on uncertainty. So this is somehow here, variational Bayes offers much more than predictive uncertainty. We're actually not looking that much into it. So I cannot point you to an amazing benchmark, unfortunately.
Yeah, thank you.
May I ask a quick question, Thomas?
Yes.
So I think you learn the distributional parameters theta, and
Yes.
when you do the inference, you need sample a lot theta
Yes.
to make prediction. But
Yes.
when we apply this to large language model, you have many different answer with long sentence. So which one you will output to the user?
you combine all of these answers. So this is here this LLM decoding process where you
and no, for classification, I understand you give the percentage like dog 90%.
No, this
cat.
is also for generating complete translations. And the idea here is to sample a different parameter and then generate a translation. And then you sample a different parameter, you generate another translation, and then you have all these, you have 10 different translations, and you can combine all of them into a single translation using this minimum base risk decoding, which is by solving this optimization problem. You have some utility function, and then based on this utility function, you can combine all these answers into a single answer.
Okay, understand. Thank you very much.
Great, thank you. So thanks to the organizers for inviting me to give this talk. I'll be speaking about quantization and some applications to distributed learning in this particular talk. So this is joint work with my former students. Nitish was a former undergraduate student and he's now a master's student at UCSD. And Ritesh Kumar was a former PhD student who has just submitted his thesis and is now working at Qualcomm. This work was funded by the Science and Engineering Research Board. So I broadly work on information theory and its applications to compression, communication, computation, and inference. And you'll see a little bit of that in this particular talk. So the motivation for this and some of the recent work that we've been doing is the following. So in recent years, we've seen a huge growth in the size of models, machine learning models that need to be implemented. So up to maybe 2018, the size of the largest models that were present were kind of growing at a steady rate, and this growth of rate was kind of proportional to the memory the availability of memory in GPUs. But since the introduction of large language models, which is GPT-2 onwards, the rate of growth of the model sizes has been much more than what the memory availability in GPUs could ever keep up. And now we're in a situation where an entire model, say GPT-4 or Llama 3, cannot be stored in a single GPU. So this has led to a number of works on how do you load part of the LLM onto your GPU at the time of inference. So this is one such example where the memory that is available is insufficient for many machine learning tasks. And I'll talk a little some other applications where something similar happens. And broadly, this comes under the class of problems of learning with communication constraints. So if we take the example of multi-GPU training, which is standard in the industry, so when you train either a large language models or any of these frontier models, these are typically trained using multiple GPUs. And since these GPUs can be run in parallel using some kind of an optimization, a distributed optimization algorithm such as stochastic gradient descent or its variants, in scenarios such as these, the bandwidth or the communication becomes a major bottleneck rather than the amount of compute that is available. You can have all of these GPUs running in parallel, computing and computing gradients in parallel, but accumulating these gradients or essentially finding the next step of the stochastic gradient descent becomes a major bottleneck because of bandwidth and also stragglers because these GPUs may not produce their mini batch gradients at the same time. Something similar at an even higher scale happens in federated learning, where you have multiple devices which want to collaboratively train to produce a deep learning model through which is facilitated either through a central server or using some kind of a communication medium. And in scenarios such as these, The communication is even more constrained. In some situations, this can also be noisy, but you still want to be able to do something that is close to what you could do when you were doing centralized training. And going back to the problem of LLM inference itself, as I mentioned, the amount of memory that is available on GPU is severely limited. And by memory, I mean there are various layers of memory in the GPU itself. But even the DRAM that is available on a GPU is fairly limited. It can go on up to maybe around, for the latest GPUs, it goes up to around 280 gigabytes, which forces these large models to be stored in memory that is outside the GPU, and you load part of these weights onto the DRAM every time you do LLM inference. So the speed of the interconnect between these on-chip storage and on GPU memory is severely limited. So this becomes essentially the bottleneck when you want to do LLM inference. So a number of solutions have been proposed for these three broad classes of problems. And broadly speaking, the solutions involve either sparsification, where you reduce the number of weights, or reduce the number of non-zero weights that have to be loaded there, thereby saving the communication that is required, or some form of sketching or low rank approximations, or what is very popular, particularly in LLM inference these days, is quantization. So I'll speak a little bit of some of the recent work that we've done on quantization in the context of distributed learning. So for this, I'd like to introduce the following very specific mathematical model, which is distributed averaging. So the problem is the following. You have n clients, and each client has a high dimensional vector. So client I has a vector x1, which we'll assume is a vector in Rd. And these clients have to communicate their vectors in a way that the server, which is a central server, can compute the empirical mean of these vectors. So the server wants to compute 1 over n times summation I equal to 1 to n of xi. But the constraint here is that you cannot send these vectors with full precision because of these communication constraints. And we'll say that each client is allowed to transmit only dr bits of information. So remember that each xi is a d-dimensional vector, and it is allowed to transmit only dr bits. And we want to work in the regime where this r is very, very small. Think of just say d bits per client, which means that essentially you can only transmit 1 bit coordinate. So we're in an extreme communication starved regime. And this sort of a model forms the primitive for various problems such as distributed learning and optimization. For instance, if you think about, let's say, distributed stochastic gradient descent, you can think of each xi to be a stochastic gradient which are going to be aggregated at the server. So the aggregate would just be the average stochastic gradient would just be the empirical average of the individual mini batch gradients. All right. So the design goal in this particular problem is to construct a quantizer, and this quantizer, formally speaking, can be modeled as an encoder which takes a d-dimensional vector and outputs dr bits, and a decoder which is going to be run at the server, which takes these dr bits per user. So it accumulates all of these n times dr bits and produces an estimate of the or an approximation of the empirical mean. So just some notation. So xi is the vector at each user, and ci is the dr bits which are communicated by each user to the server, and mu hat is the estimate of the empirical mean that is produced at the server by observing these n times dr bits which are communicated by the clients. And So we'll have two constraints. We want to design these quantizers in order to satisfy two constraints. First, we want unbiasedness. So we want this estimate of the mean that is produced at the server to be an unbiased estimate of the actual empirical average. So underlying this, we're assuming that these encoders and decoders can potentially be randomized functions. And in fact, they have to be randomized functions. And we want this estimate to be a very good representation of the actual mean. So we want, and we'll measure the reliability in terms of the normalized mean squared error. So it's essentially the mean squared error, which is normalized in order to account for scaling differences among the different vectors. So we want to design a quantizer that is unbiased and also has low normalized mean squared error. There have been a number of works that have looked at this particular problem, starting with quantized stochastic gradient descent way back in 2017, which proposed a scheme that achieved a normalized mean squared error that scaled as order square root of d divided by n. And it was also an unbiased scheme. Following that, there have been a number of works which tried to reduce the normalized mean squared error, but using an additional resource, which is shared randomness. So you assume that some random bits are shared between each user and the server, and you use this to design an unbiased quantizer or unbiased estimator of the mean that achieves small normalized mean squared error. So typically, most of the prior works required shared random bits that scaled with the dimension. So for example, the latest work in 2024, this achieved a normalized mean squared error of 1 over n, but it required a certain number of random bits to be shared between each user and the server, and the number of bits required scales linearly with d. So in a communication starved regime where, let's say, each client or each user is allowed to send only roughly d bits of information from the user to the server, this additional shared randomness also requires some amount of communication, which is expensive. So this is not really feasible. So in our work, we achieve the state-of-the-art normalized mean squared error, but this requires absolutely no shared randomness and also produces an unbiased estimate. And as we'll see, this is also a very computationally efficient solution. So the high-level approach that we use is the following. Essentially, each vector xi is going to be quantized independently of the others using an unbiased quantizer. I'll explain what I mean. So at each client, or each user does the following. So it takes its own d-dimensional vector xi, and then it produces two quantities. So first, it normalizes xi to produce a vector v. So it's normalized specifically by the L1 norm. So you take xi and then you normalize this by the L1 norm to get a vector v which has unit L1 norm. And this v is going to be quantized using an unbiased quantizer. So each client transmits two quantities, one which is a single real number, which is the L1 norm of x, and roughly d-bit representation of v. And we'll see how to get this d-bit representation of v. And recall that we want to design this whole system such that we get an unbiased estimate. So at the receiver or at the server looks at these roughly d bits and outputs for each user an estimate xi hat. And we want this xi hat to satisfy the property that the expectation of xi hat is equal to x for every x in RD, but you can it's sufficient to consider vectors in the unit L2 ball. At the same time, we want the normalized mean squared error to be small, which effectively reduces to requiring the mean squared error between this xi hat and xi to be as small as possible. So we want to construct, so effectively, the problem now reduces to constructing an unbiased quantizer for this vector V, which lies in the unit L1 ball. So that's what much of this talk is going to be about. How do we design an unbiased low MSE quantizer for the L1 ball? And specifically, we'll be using, so since we want a quantizer for the L1 ball, effectively, we want a set of points, a discrete or a finite set of points in the L1 ball that will be representatives for each of these. So these will be the corresponding quantization representatives. So I'll define the following quantity, which is the set of all generalized M types. So the set of generalized, so an M type is essentially a vector, which is a ratio of an integer to an integer M. So each entry of this M type, which is basically a vector, can be expressed as a ratio of two integers, with the denominator being equal to some fixed positive integer M. All right, and we will use this as a code book essentially for quantizing the L1 ball. So geometrically, in 3 dimensions, the L1 ball essentially is an octagon, essentially the surface of the octagon, and each point on this octagon is going to be mapped to one of these discrete set or this finite set of points. So why look at this specific code book? There are a number of advantages. One, some of the properties of this code book has been well studied in other areas or in other problems in information theory. And the second computational advantage is that each vector, each of these points can be expressed as a ratio of two integers. So if you want to perform any operations on these quantized points, it is sufficient to just use integer arithmetic. So that also gives a computational advantage. So now, given this particular code book, how do we quantize any vector to one of these points in the code book? So the first approach that one might think of is, all right, if you want an optimal quantizer, then what you could do is, given any point on this L1 ball, you map the point to the closest point in this code book. So take any point on this octagon, you map this to one of the closest green point that is available in this particular octagon. However, that's not a good idea if you want an unbiased quantizer. This will ultimately just give a biased quantizer, and we specifically want an unbiased quantizer. I'll briefly explain how we can actually achieve unbiased quantization using this particular codebook. The intuition is the following. So you have this vector V, which lies on the unit L1 ball. You can express this as a product of two vectors, an entry-wise product of two vectors. So since this is a vector on the L1 ball, if you remove the signs of this particular vector, then what you end up with is simply a probability vector. So P is a vector where all of the entries are non-negative, and the sum of the entries is equal to 1. So if you discount for the signs, then effectively quantizing V corresponds to quantizing a probability vector. And I mean, if you think about it geometrically, remember that the L1 ball is, the unit L1 ball is basically the surface of this particular octagon. And you can specify any face of this octagon using one of the 8 configurations of signs. And so quantizing the surface of this entire octagon we can essentially be reduced to quantizing just one face of this particular octagon, which corresponds to the probability simplex. So we've come down a sequence of steps. We started with wanting to quantize vectors, and that has reduced to quantizing the L1 ball. which now is reduced to quantizing probability vectors, and you can represent each probability vector as a sum of the integer part and the fractional part. And the goal is to essentially quantize this fractional part using a carefully chosen set of 0, 1 vectors. So there's some, in particular, we'll quantize this using 0, 1 vectors of a particular Hamming weight. So I'll maybe not getting into too much of the details, but essentially, since we want to construct an unbiased quantizer, what we do is we randomly, the fractional part of this probability vector is quantized using a randomly sampled 0, 1 vector from a particular set. And we show that this can indeed be done. But the geometric intuition is the following. So let's take a probability vector that lies in this particular simplex. The set of green points is our codebook, so to speak. Now, this vector can be expressed as a convex combination of all of these green points put together. Obviously that much is clear. However, remember that our goal is not just to produce an unbiased quantizer, we also want to produce a quantizer with low mean squared error. So quantizing P, so essentially given a P, an unbiased quantizer would produce one of these green points with a certain probability while ensuring that in expectation, this is equal to P itself. But if you choose the distribution wrongly, then it could lead to high mean squared error. So it makes more sense to express P as a convex combination of some subset of this particular codebook, which is precisely the subset that is mentioned over here. So the goal is to express this P as a convex combination of some subset of points that lead to an unbiased estimate with low mean squared error. But the question is, can we do this computationally efficiently? And the answer is yes. So we have a computationally efficient sampling algorithm, and this can also be encoded and decoded very efficiently. In the interest of time, I will not go into too much of the details, but I can get back to this if there are any questions. So for this particular quantizer, we have bounds on the achievable mean squared error. We show that essentially that the mean squared error for quantizing any one of these vectors, the normalized mean squared error is essentially some constant. So in the context of mean estimation, what this translates to is that the normalized mean squared error grows as order 1 over n. And the communication, we can also bound the number of bits that is required to communicate one of these code word points. This can be done very efficiently, and we also have bounds on the communication complexity that is required. Here are some empirical results to show to quantify the performance of our particular scheme. So we plot the normalized mean squared error for various distributions. And for this is an example where we look at d-dimensional vectors of dimension, I think in this case it was 2048, and these were quantized using various algorithms. When you take the Gaussian distribution, it turns out that our scheme is not the best. It's the second best performing scheme. That's precisely because some of the best performing schemes either use a higher number of bits. In this case, the best performing scheme is scalar quantization, but with R is equal to 4. So you're transmitting 4 bits per dimension. But you can get pretty close to that using far fewer number of bits using our scheme. And these are for other distributions, the Laplace and the log normal distribution. And in this case, we see that for log normally distributed vectors, our scheme outperforms a scheme with say 2 bits per dimension, does even much better than scalar quantization with 4 bits per dimension. Here are some results for some sort of toy data sets, federated learning on fashion MNIST and CEFAR 10. There's not much that you can take away from this except for the fact that even when you're operating at very low bit communication regimes, our scheme and in fact many of the other schemes also perform extremely well. So even though you're trying to do distributed learning with extreme communication constraints, you can still get reasonably good performance, provided you design your quantizers carefully enough. So here's some future work. So what we've done is basically we just looked at federated learning with some toy data sets, but you can also go beyond toy models and also analyze other distributed stochastic optimization algorithms. And we are also interested in seeing how these quantizers can be used for LM inference, in particular for compressing transformer architectures. And there's still many open problems in theory as well. For example, deriving tighter lower bounds on the MSE. Perhaps what I didn't mention earlier is that our scheme is order optimal in the sense that you can't improve the dependence on D or N for the quantizers, but the constants could essentially be improved. So the construction of an optimal lattice quantizer for the L1 ball, it's of course a hard open problem, but it still remains open. So I'd like to stop at this point, and I'd be happy to take any questions.
Yeah, thanks for great talk. Any questions from audience? May I ask a question? So
yes, please.
You talk about unbiased, the estimation.
Correct.
It's about the model prediction unbiased or the parameter unbiased?
So basically, I'm thinking of this setup in the context of, say, distributed stochastic gradient descent.
Yeah.
So what you're transmitting, so what each client has is a stochastic gradient, which is an unbiased estimate of the true gradient. So what I want is essentially that even after quantization, I still get a stochastic gradient, essentially. So it's a quantized stochastic gradient. That's where the requirement of unbiasedness comes from. And this is more crucial for problems such as distributed stochastic optimization and federated learning, maybe not so much in, say, LLM inference.
Okay, I see. So that means if the gradient is unbiased, we can keep the performance, the final model performance comparable.
Correct. Also, because you want, since this is what you're running is an iterative process, right? So distributed stochastic gradient algorithm. If there is, let's say, if you use a biased quantizer, then what can potentially happen is that when you run this algorithm for many rounds, the bias can accumulate, which means that the algorithm doesn't converge. So the unbiasedness ensures that the algorithm is guaranteed to converge.
Okay, got it. Thank you. Okay, if no further questions, thanks again, Shashank.
Thank you.
Hello, everyone. My name is Futoshi Futami from Osaka University and RIKEN AIP. Today, I will talk about the uncertainty quantification, especially focusing on the calibration in classification. Calibration is a kind of the concept which quantifies the reliability of our prediction of our machine learning models. And today's talk is focusing on some gentle introduction of the calibration and introduce our recent several works shortly. As you know, deep neural networks are highly successful in various tasks, including the classification problems. And in classification problem, typically such models first output the predicted probabilities for each class, and then predict the class level by selecting the highest predicted probability classes. And then in this kind of setup, in addition to the predicted class level themselves, these predicted probabilities are highly useful for decision-making scenarios, especially high risk scenarios. One example is the medical diagnosis, such as the cancer recurrence prediction problems. For example, by estimating the probability of disease recurrence, we can make the optimal treatment decisions. This is because that in such a high-risk decision-making scenario, each decision is associated to a different costs or risks. For example, if the cancer has actually recurred, but no treatment is given, it is an overlooking of the disease, which is, of course, fatal for the patients. And conversely, if treatment is conducted, but there is no actual recurrence, then it is a medical accident, and of course, it is very harmful for the patients. So the consequence and risk of the decision are not equivalent. Under this kind of heterogeneous risk setting, to derive an optimal decision, we need to weight these different risks with associated probability. Another concrete scenario is the finance. For example, estimating the probability of default, estimating the default rate. By estimating the default probability, we can derive the optimal decision, that is, whether we should render money to a specific group or company or person. And similar to the medical setting, we require some associated probability to derive the optimal decision. And since the actual probability or underlying distribution is unknown in practice, we instead use the predicted probability as a surrogate in practice. And in such a situation, we implicitly assume or we implicitly hope that predicted probability will approximate the actual probability or distribution. And this concept is elaborated by the notion of calibration. Calibration measures how well the model's predictive probability aligns with the actual frequency of the true level or conditional probability. And in the case of the binary classification here, let's assume that we have some hypothesis, for example, neural network that outputs the predictive probability that the input feature has the class level 1. Then calibration is formally defined as follows: that observing the event that our model outputs the score P, then we hope that actual level frequency conditional on such event equals to P. And this relation holds for all P almost surely. We say that our model is perfectly calibrated. And in the binary classification, this relation is equivalent to say that if our hypothesis outputs the probability P over some event, then the accuracy over such event is P. And if this kind of relation holds, we can use our predicted probability as a moderate surrogate for the downstream decision task. But unfortunately, calibration does not hold in many situations. Actually, calibration strongly depends on the algorithm and the model and the data we use. And it has been reported that many neural networks are often not calibrated. This is a very simple example, but for example, when using this kind of very simple model, let's see the point where the output score FWX is close to 1. Here, the actual level frequency conditional probability corresponds to this blue line, and it is almost like the 0.1. So around this region, FWX is close to 1, but this conditional probability is 0.1. So clearly, calibration doesn't hold here. And similar phenomena is often reported to various neural networks. And interestingly, high accuracy does not necessarily imply good calibration. And also, well-calibrated model does not guarantee high accuracy. So we need to take care of them separately. Then, I think the research about calibration has two important directions. The first one is that how to measure the calibration accurately. So our goal is to evaluate the discrepancy from this relation. And as I will explain later, this is not so simple. And the second research question is how to correct uncalibrated models. I think this is decomposed into two sub-problems. One is to understand when models are well calibrated and also achieves the high accuracy. And the second point is developing the efficient algorithm for the recalibration or correcting our models. This means that how to improve our model's calibration performance without retraining it and without sacrificing the accuracy. And this step is also known as the post-processing. I will explain them later. So first, I will explain this first topic, how to evaluate the degree of calibration. First, I will explain the problem setting. Given some data set, in the standard running scenario, we split the data into training data set and some held out test data. And then we train our model using the training data. And we evaluate our model's calibration performance using the held out test data set. And what we want to do is to evaluate the discrepancy from these relations. And I think the most widely used and most widely known metric is the expected calibration error, which is also known as the EC. And it is defined in this way. And this is the simple L1 distance between this conditional probability and this output score. So in this way. And actually, this is as you can see, this is a population static. So we need to construct the estimator, which is based on the test data set. So when constructing the estimator, the key is how to estimate this conditional probability. To estimate this conditional probability, I think the most widely used approach is the binning EC, where we consider the local empirical average defined by bins. So formally, in the binning EC, we first split the 0-1 probability interval into B small regions, B small intervals called as bins. Then we take the empirical average of level inside each bin. Then such empirical average correspond to some kind of non-parametric estimate of this conditional probability. And then we aggregate errors over all bins. And I think if you use a famous deep learning framework like PyTorch, and if you call EC function, then usually many framework implements this binning EC as the EC. So now we have the estimator of this EC as the binning EC. We can evaluate the degree of calibration. But this binning EC is the estimator, so we need to understand the bias of this estimator. Actually, that bias strongly depends on how we prepare bins and the number of bin B. And this is a bit technical point, so I will skip the detail. But under some smoothness assumption, we can analyze the bias of the binning EC. I will skip the detail, but the bias can be decomposed into the binning bias and the variance owing to the finite samples. And as you can see, this B is the number of bins, and this B plays some kind of a trade-off between the bias term and the variance term. And by setting the optimal bin scale in this way, we can get some kind of bias order in this way. Actually, this rate is the minimax optimal, so we cannot improve this. And this part is a bit technical, but in any way, now we understand the degree of bias. We can use the binning EC safely. And by using the binning EC, we can evaluate the EC. And if after evaluating the binning EC, and our model shows the large binning EC, then we need to correct our model. So this is the second research question. which I mentioned, that is how to correct uncalibrated model. However, in this step, we do not want to retraining our model since it is time consuming. Instead, usually we consider post-processing approach. It is called as the recalibration. Here, we fix our original model FW and we prepare post-processing function eta, which is run by the independent recalibration dataset here in this way. And then final prediction is given by this composite function of our original model and recalibration function eta. As for the class of this eta, one approach is to use the simple parametric functions. There are various approaches, including the Plateau scaling, or temperature scaling, or beta calibration, and blah, blah, and so on. And although there are various approaches, I think this post-processing function is relatively simple compared to the baseline function f. Another common approach is using the non-parametric method or semi-parametric method for the recalibration, like the histogram binning or isotonic regression. Actually, those recalibration is a kind of the learning problem over the recalibration data. So we need to consider the following question. If our model shows the small binning EC over the recalibration data, then is it also possible to achieve the small EC for unseen test data? So this is the kind of the problem of generalization in a sense of EC. So since this is a problem of the generalization, we can analyze such bias using some kind of statistical learning theory. Here, this result is based on assuming that if our recalibration function is parametric, then we obtain this kind of generalization error gap. Actually, this is just the theoretical analysis, but this kind of analysis can be used to derive some recalibration algorithms. Last year, we derived the similar generalization bound using the Bayesian theory. And some of you might know that the Bayesian theory is suitable treating the probabilistic models. So we develop a generalization-aware recalibration algorithm combined with the variational inference based on the Gaussian process to get the new recalibration algorithm. But this topic is very advanced, so I will skip the detail point. So far, I mainly focus on the binning EC, but nowadays, many drawbacks are reported in the binning EC. There are various drawbacks, but from the practical viewpoint, I think the most unfavorable point is that the binning EC is very sensitive to the choice of bin size B. I will skip the explanation of numerical result, but actually binning EC is very sensitive and very difficult to choose the appropriate bin size. So it is unreliable and unstable. So nowadays, many researchers try to find out the alternative metric which can capture the calibration more accurately. And several alternatives have been proposed, but I believe one of the most promising alternative is the smooth calibration error here. Actually, this definition seems a bit difficult, but intuitively, this metric measures the calibration by using the inner product between the test function h and the deviation of the level and output probability. And this test function is from the family of Lipschitz function class. In other words, this metric measures the calibration in a following way, that how much we can detect the miscalibration by taking the inner product using the Lipschitz test function. And interestingly, if our underlying conditional distribution py given fx is smooth, then this smooth C is almost equivalent to the original EC. And this metric is smooth and continuous, as the name says. So it is easy to estimate. And what is more interesting is that if we replace this test function class to, for example, RKHS or polynomial function class, then we can get the various interesting metrics. But today I will focusing on this lipstick function class. And then, given the test data set, we get this kind of finite sample estimator. You can see that there is no hyperparameter to be tuned. And actually, this supremum problem is just the convex optimization. So we can solve this efficiently. For example, if you use a Python, you can just call the convex optimizer like the civxopt to solve this. And what is more favorable is that without the smoothness assumption, we can assure the statistical bias in this way. And this bias is better than the binning EC. Then I will move on to different topic of calibration. That is to understand when models are well calibrated and also achieves the high accuracy. Actually, calibration itself is a rather weak criterion because, for example, when using this kind of class prior as our predictor, actually we can achieve the perfect calibration. But of course, this kind of predictor is completely useless because this neglects the input feature. So we need to consider the calibration and accuracy simultaneously in practice. And for this question, I do not have the conclusion, but I will introduce our recent work in the following slides. This work will appear in this year's ICLR, but here we analyze when we can achieve the high accuracy and well-calibrated model simultaneously using the statistical learning theory. That is, we decompose the population smooth calibration error into the smooth calibration error over the training data and generalization error in a sense of the smooth calibration error. Then we have shown that the smooth calibration error can be smooth calibration error over the training data set. Here, the first term can be upper and lower bounded by the inner product between the test function and the function gradient. Here, function gradient implies the loss gradient with respect to the logit function when we use the cross entropy loss. Here, G is the logit function and sigma is the sigmoid function. So we convert the output of the logit function into the probability by using this sigmoid function. So in this way, smooth calibration error can be controlled by the function gradient. So this motivates us to expect that some algorithms that controls the function gradient can achieve a good calibration performance. And as you might know that the representative algorithm, which using the function gradient is the gradient boosting. You know that in the gradient boosting, we iteratively update the logit function using a base runner. Here, we update the logit function using the base runner with a step size W. And update direction is usually obtained by approximating the function gradient using this base runner. For example, usually we iteratively minimize the cross entropy loss, and in the most basic gradient boosting algorithm, we consider the quadratic upper bound of the cross entropy loss. So choosing the base runner is a problem of the regression problem using a squared loss where the target is the function gradient. So we minimize this squared loss where the target is the function gradient, and we use the base runner. And common choice of base runner is the shallow regression tree. So in each step, we iteratively minimize this. We iteratively solve this regression problem in the gradient boosting. And then, under this boosting setting, we analyze the calibration performance of the gradient boosting tree. And for that purpose, we assume the some margin assumption, which is common when analyzing the boosting algorithm. But I think this is a bit complicated, so I will skip the explanation of this assumption. But intuitively, this assumption implies that at each step of the gradient boosting, we can find a well-correlated weak runner to the function gradient. And then, under this kind of setup, we can upper bound the training smoothly in this way. And there are various parameters to be analyzed, but the key message here is that if the step size is set to the 1 over square root t, where t is the iteration number, then training smooth calibration error converges to 0. So from the algorithmic viewpoint, gradient boosting can control the training smoothly. Then let's go back to the previous decomposition. Now we analyze this first term. And then what we have to do is to analyze this term. And interestingly, we can extend the standard empirical process theory to the smooth calibration error. And we can upper bound this generalization error by the sum of the complexity of the Lipschitz function class and the complexity of our base hypothesis class. And then by combining these analyses, we get the final conclusion. That is, we can simultaneously control the misclassification rate and calibration performance. That is, for any epsilon, where this implies that we can guarantee the epsilon small calibration error and epsilon small misclassification. We can achieve the epsilon small calibration error and epsilon small misclassification rate by setting the iteration and step size and training data in this way. And as far as we know, this is the first result that simultaneously guarantees the misclassification rate and calibration performance in the gradient boosting tree. And this result is for the gradient boosting tree, but we derive the similar result for the kernel method and some simple neural network where we consider the two-layer MLP. And in this way, nowadays, some algorithmic study for calibration is getting more and more popular. And other than our work, you can find other theoretic papers focusing on calibration. This is a summary so far. I've introduced the concept of calibration, and I also introduced some theoretic analysis for that. Finally, I will remark the calibration of multi-class setting. So far, I mainly focused on the binary classification, but of course, we can consider the calibration for the multi-class setting. But in multi-class setting, we need to take care about the metrics we use. So first, I will explain the basic notations. Here, we consider the K-class classification problem, and we have some probabilistic classifier, which outputs the K-dimensional simplex. You can assume for example, softmax function. And fxk implies the confidence of level k-1. And we predict the level by taking the argmax of our output scores. And actually, there are several options to evaluate the calibration error. The most naive approach is just extend the EC from the of the binary classification. So we just consider the L1 distance for this. But unfortunately, this metric suffers from the curse of class size, similar to the binary class, similar to the curse of dimension. So usually nobody uses this metric. Instead, I think the most widely used metric is the top calibration error, where we only focusing on the top class we use for the prediction. So this is the one-dimensional problem similar to the binary classification setting. And also, widely used metric is the marginal calibration error, where we simply check the degree of calibration in an element-wise way. And actually, we can derive this statistical bias by assuming the, for example, smoothness assumption. And as I said, naive extension of the calibration EC to the multi-class setting suffers from this kind of bias. So this is a curse of class. This is a curse of class size. So it is hopeless to use. And instead, when we use the top calibration error, so this is almost equivalent to the setting of the binary classification. The rate is slightly improved. And however, in some practical cases, guaranteeing the top class or marginal class are insufficient. In such cases, we need to develop more sophisticated metrics. And also, we can define the smooth calibration error for the multi-class setting. However, it is known that we cannot compute the multi-class smooth calibration error efficiently. So still, many researchers are working on developing nice calibration metric over the multi-class setting. I think the notion of calibration is relatively old, but nowadays the research is gaining popularity. So I will be happy that some of you get interested in this field. So thank you for the listening.
Yeah, thank you for the great talk. Due to the time limit, maybe just one quick question. Futoshi, can you see the chat box?
What assumption does calibration rely on about the model or data distribution? This is a good question. For example, when we consider evaluating the degree of calibration, so like this, then to estimate this EC accurately, at least we need some kind of smoothness assumption. Otherwise, our finite sample estimator can be biased severely. But when we use the smooth calibration error, which I introduce later, we do not need such smoothness assumption. And as for the second question, how does the calibration behave in out of distribution data? This is also a very good question. In today's talk, I only focus on the in distribution setting. And there is some research how we can extend the metric of calibration to the out of distribution setting. But I think I think those works still relies on many unrealistic assumptions. So I think there is no consensus in the community. So it is still ongoing work. I think you can find many research papers, recent conferences. So I'm sorry, this is not the answer, but this. So yeah, so that is the situation of this field.
Yeah, thanks again, Futoshi.